All right, so yesterday we left off talking about the chi-squared test, and more specifically the chi-squared goodness of fit test. There's going to be a few more that we learn about. So the chi-squared distribution comes in different sizes, and those sizes depend on the degrees of freedom. We get a chi-square statistic, just like the z and the t, that tells us how far out we move along this x-axis, and we calculate the area under these distribution curves in order to calculate the p-values. Again, that p-value will tell us what to do. So how unusual was the sample? For these types of tests, we're wondering, when will it follow a chi-squared distribution? So a chi-squared distribution will be followed when three conditions are met. Two of them are going to look very familiar. This first one is some form of randomization. So the data needs to be obtained randomly, and the reason for that is because I want to be able to apply my findings to the whole population. If I, for example, go into the penny bin and grab 20 of the shiniest pennies in there, well, that wasn't a random sample. So if I then come forward and say, hey, the true average year on the pennies is 2005, well, that's not representative of the whole population. So my findings can't be applied. So random allows us to apply the findings to the population. And that can be satisfied in a couple different ways. We can have a random sample or randomized experiment. Okay, we'll skip the second one, we'll come back to that. 3 will look familiar. 3, I want to stay under 10% of the total population. And that is only when I'm sampling without replacement. So that's like standing outside of a grocery store or calling people. Calling people is a bad example because there's other issues with that. But that's the idea there. So experiments, we don't necessarily have to satisfy this condition. I've said this before in class, you can always check this condition without losing points. So I think it's easier to just always remember the 3 conditions rather than the 2 conditions or the 3 conditions and then remembering when the 3rd condition needs to be applied, but that's up to you. Well, let's talk about the second condition. The second condition is the new one, and this one, just like when we were talking about a 1 proportion or a 2 proportion, we needed to know that we were going to see at least 10 successes and at least 10 failures. Well, similarly for these proportions, where we're talking about proportions across multiple categories, we need to know that we expect to see at least 5 of everything. Okay, so the expected count in each cell is greater than or equal to 5. Okay, so I'll add the equal then, or equal signs for both of these. And so what I mean by greater than or equal to, the expected count, so let's come back to the M&M example. For the M&M example, the expected counts were these values right here. I expected in that bag to see at least 5 blues, to see at least 5 browns, to see at least 5 greens. So the 5 count condition was satisfied for this example, which was why we were allowed to move forward. That is the only new condition, and it's got to be in place every single time we run one of these chi-square tests. Okay, so let's see another example. Police records have shown that of all stolen cars, 15% are white, 15% are blue, 35% are red, 30% are black, and 5% are other colors. So for this example, the researchers took a random sample of 830 stolen cars, and their observed colors were listed below. We want to know, does the sample indicate that the police records are true? So we have a hypothesized distribution, which are these numbers up here, and then we have our alternative, that it's different. That's our hypothesized. Okay, so let's first just go ahead and state the null and the alternative. The null hypothesis is that the distribution is what we think it is. So the distribution of colors of stolen cars follows the distribution in the police records. Okay. Well, the alternative is that it doesn't, that it follows some other distribution. So the distribution is different than, sorry, let's specify what distribution. The distribution of colors of stolen cars is different than the distribution in the police records. Okay, now that we've got our null and our alternative, we just have to check those conditions and we're done with the state step. So for the first condition, it was stated that it was a random sample. I'm not going to say SRS, because unless it said it was a simple random sample, that's like a very special brand of random sample. I'm just going to say exactly what it told me. So if it said it was a random sample, that satisfies the condition. Condition number 2. Let's talk about condition number 2. So I need to see at least 5 white cars as expected. I need to expect at least 5 blue cars, at least 5 red cars, at least 5 black cars. So how are we going to do that? Well, in order to do that, let's go ahead and input the data into our calculator. So you guys will probably need a second to do that, but I already have it here, so ask the sub to pause the video if necessary. But here you'll see, and please be very, very careful with the order in which you put these in, because the order for the word problem, so the order that's been highlighted up here, is different than the order that the observed are listed. So the way that I have it put into my calculator, just make sure yours match. So I have white, blue, black, red, and other. Okay, then over here in list 2, I have the expected proportions. So if I want to find the expected counts, I'm just going to take all these numbers and I want 15% of 830. Those will be all the expected white cars. I want 15% of 830. Those will be all the expected blue cars. 30% of 830, and so on and so forth. So I'm just going to take all the values in list 2 and multiply them with the 830 cars in my sample size. So list 3 is now my expected values. So I'm going to just go ahead and record that over here. L3 equals expected values. Just so I have that, you can just put it somewhere off to the side or not necessary. Okay. So thinking about condition 2, are all of these values in the expected cells? When I say cells, I'm just referring to these little blocks in the table. Are they at least 5? Well, yes, we can see that right away. So condition 2 has been met. Oops. The expected number of each color of stolen car is greater than 5. And then finally, condition 3, we would have to check that one since it is a random sample. I'm going to say there are more than 8,300 cars that get stolen. Okay, so now we've finished our state step. So we're finished with our state step. Let's go ahead and move on to the plan step. The plan step is pretty short. We just have to tell the reader what type of inference method we're using. So the inference method I'm going to use, and hopefully you guys will choose the same one, is a chi-squared goodness of fit test. You can also choose to call this a chi-squared GOF test. Both of those are acceptable. I, from here on out, will probably call them a chi-squared GOF test because it's shorter. All right, and that's it for the plan step. Now, for the do step, let's go back to our calculator because I need to actually calculate that chi-square value. If we'd like, we can draw a picture here. Just please be careful with your picture. I need to know for this chi-squared distribution, what was the probability of seeing a sample that unusual? So it starts at 0, and I'm going to get some chi-squared value. And I don't know what that is. I have to look at my data. Okay, so coming back to our calculator, the first step, if we're thinking back to the M&M example, would be to do observed minus expected. Well, observed are in list 1, expected are in list 3, so I'm going to take list 1 and subtract it from all the values in list 3. If you're having trouble following along, I'm going to go a little bit quickly through these next calculations. Keep in mind the key press history is all right down here, so you can refer to that as well. All right, so L1 minus L3 gives me the O minus E. I now want to square all of these values, so every single value I'm going to square in list 4. Let's go ahead and square those. All right, and then I just need to divide those squared values by their respective expected values. And so those are in list 3. So I'm going to take list 5 and divide it by list 3, just like we were doing in the M&M table yesterday. All right, so L5 divided by L3. And here are each of my individual measures of unusualness. So I add all of these up to get my chi-square value. So if you add all of these up, we'll notice real quick that the other category was very, very unusual. But once we add all of these up, that will give us our chi-square value. And you guys can take a second to do that. If you have the sub, pause the video. Otherwise, I'm going to keep going. Once you add all of these up, you should get 66.2, give or take some rounding. So I'm going to record that in the do step. Let's change the color. All right. So the chi-squared value is 66.2. And if we come back over here, my degrees of freedom are the number of categories minus 1. So there were 5 different categories, so degrees of freedom determines the shape of this curve over here, and that number is going to be 4. So what I'm going to do is chi-squared CDF to determine the area under this chi-square distribution, and that will be my p-value. And so just real quick, this is the probability of getting a chi-square value greater than or equal to 66.2. So in our calculators, we'll go to second distributions and go all the way down to option 8. Option 8, we want 66.2 all the way over to a bunch of 9s, degrees of freedom, and paste. Oops. Hopefully you guys didn't do that. We want to be in our home screen before we do that. So second vars, now option 8. Value should still be in there. And we paste and get our p-value. So we can see that that's pretty low. We've got 1.43 times 10 to the 13th power. So we'll go ahead and report that. .4, and we'll go ahead and round. 1.44 times 10 to the negative 13. So we're hopefully comfortable enough with p-values to know that that is very, very low. Now, that will lead us right into our conclusion. Okay, so we're going to conclude. I'll go ahead and make that darker. Yellow's a bad idea. Let's do purple. Okay, so we're going to reject the null. It's very, very unlikely that we would see a sample that weird if the null was true. So we reject the null because the p-value is less than any reasonable significance level. Or, since if the null, let's read that. This would be your other justification. So, or because if the null was true, the chances of seeing a sample this or more unusual would be let's just say less than 1%. So that very, very small p-value right here represents the chances of seeing a sample this or more unusual. And so that could be your alternate justification. Again, decision and justification, and then our second sentence is reporting if we found evidence. Well, we did find evidence. So we have sufficient evidence that the null is true. So I'm just repeating my null, my alternative, sorry, excuse me. We have sufficient evidence that the alternative is true. So that's all I'm doing. I'm going to repeat exactly what I said my alternative was, because that was what we just kind of found a case for. So we have sufficient evidence that the distribution of colors of stolen cars is different than the distribution in the police records. Okay, and we'd be all done with that problem. Now, some of you may have been perusing your calculator and found something. This is a significance test that we just ran, but I haven't actually gone to the test section of my calculator yet. So some of you might have explored that already, and you'll see that there is, in fact, a calculator shortcut. So let's go ahead and repeat the do step as though we'd done the calculator step. So again, you can do it by hand by doing chi-squared CDF, or we can do it with a calculator. So if I do it with the calculator, I'm still responsible for reporting all the same values, but now I don't have to add up all of the chi-square values, or I don't have to add up all of the squared values and find the summation to get chi-squared. So all I have to do is go to, let's start over, from your home screen, you're going to go to Stat, Tests, and if you go up, it's a little bit faster because it's close to the bottom, chi-squared goodness of fit test. We'll select that one. And then keep track of where you've stored your observed and your expected. My observed are in list 1, my expected are in list 3. This is a degrees of freedom of 4. And I'll calculate. So we calculate, and we get the exact same, or roughly the exact same, with give or take some rounding, a chi-square value of 66.3 with a p-value of, again, 1.35 times 10 to the negative 13. So these three values right here at the top, those need to be recorded for full credit. You'll see down here, this right here, CNTRB, those are the individual squared observed minus expected divided by expected. So this would be, I believe, list 6 in your calculator. Okay, so these first three are the ones we're reporting. So just with our calculator, we'll jot down exactly what we had before. So we had a test statistic of 66.3. We had a degrees of freedom of 4, and we had a p-value of very, very low 1.35 times 10 to the negative 13. Our conclusion is still the same, just two different ways of completing the do step, just like we've seen in the last couple units. Okay, so I know that was pretty quick. This is on YouTube if you'd like to watch this example again. Otherwise, for the remainder of the period, go ahead and try the example on page 4. If the period is very close to ending, please go home and do part 4 for homework over the weekend. We will be going over the answers to that in class on Monday. I will not be going through the entire problem. I will only be addressing specific questions from people who tried the problem over the weekend. Okay. that's it. If you have any questions, you can send me an email. Otherwise, have a fantastic weekend.